Hello again. You may remember in the last video we defined the average rate of change in f on the interval from a to x as the slope of the corresponding secant line given by this formula, f of x minus f of a divided by x minus a. We also defined the instantaneous rate of change in f at a as this limit, the limit of f of x minus f of a divided by x minus a as x approaches a. Now, what I want to do in this video is come up with an alternative definition for both of these. And we're going to do that using this diagram. So in this diagram, we have the graph of some function f of x that looks like this black line. And let's say we want to find the average rate of change in this function from this point A and a point that's a little bit larger than A that we're going to call a plus h. Now, in order to find the average rate of change between these 2 points, what we're going to do is we're going to draw a line between these 2 points. And whatever the slope of that line is the average rate of change in the function between those 2 points. Okay, notice this point right here is located at the ordered pair a comma f of a, and this ordered pair over here is at a plus h comma f evaluated at a plus h. Okay, and now to find the slope of this line, we just need to take the rise of the line divided by the run of the line. And I think you can see the rise of this line would be f evaluated at a plus h minus f evaluated at a. That's the distance between here and here. And then the run of this line would be the distance from here to here, which is just a plus h minus a, which is simply h. Okay, so if we take rise divided by run, we get this. And that's the slope of this line, which is the average rate of change in this function from this point to this point. By the way, this is called a secant line. A line that goes through 2 points on the function is called a secant line. And so that's also the slope of this secant line. Okay, so then let's turn our attention to finding the instantaneous rate of change in this function right at a. Okay, so the way we're going to find the instantaneous rate of change in this function right at a is we're actually going to look at the secant line that goes through these 2 points. In fact, we're going to look at several secant lines that go through 2 points on the function. What we're going to do is we're going to let this point get closer and closer to this point. And as that happens, we're going to look at the slopes of the secant lines. And whatever number the slopes of those secant lines approaches is the instantaneous rate of change in this function right at this point A. Okay, now notice as this point gets closer and closer to this point A, the distance between the 2 points is getting smaller. Okay, in fact, it's approaching 0. So that this h is the distance between the 2 points. H is heading towards 0 as this point gets closer and closer to A. Okay, so as h is going to 0, right, h is getting smaller and smaller, notice that the secant lines are approaching this red line. And that red line is called the tangent line at this point A. In fact, the slopes of these secant lines are approaching the slope of this red line, this tangent line. And whatever number the slopes of these secant lines is approaching is the slope of this tangent line, which is also the instantaneous rate of change in the function right when x is equal to a. Well, what is that number? Well, that number is the limit as h goes to 0 of the slopes of the secant lines, and the slopes of the secant lines are equal to this, right? F evaluated at a plus h minus f evaluated at A divided by h. Okay. Okay, so the instantaneous rate of change in this function f right at A is equal to this limit as h goes to 0. And that's also equal to the slope of this tangent line right at A. Okay, so we have two alternative definitions for the instantaneous rate of change in a function at A, and also for the average rate of change in a function between 2 points. Now, our earlier definitions, if you need to refer to them, were these definitions. They'll give you the same answers, and now we have alternative ways of defining both of these. Okay, so what I want to do now is just do an example where we use the alternative definitions. Okay, so let's look at example 3. In example 3, we want to find an equation of the line tangent to the graph of this function, x cubed plus 4x, at the point 1, 5. And I want to use the alternative definition of the slope of a tangent line to do this. Okay, so the slope of the tangent line to this function at this point 1, 5 would be equal to this limit, the alternative definition at least. So it's the limit as h goes to 0 of f evaluated at a plus h minus f evaluated at a, all divided by h. Now in this case, notice a is equal to 1, because that's where we're trying to find the tangent line at, right? We're trying to find it at the point when a is equal to 1. Okay, so let's find this limit. Okay, so it's going to be f evaluated at a plus h, but a is equal to 1, right? So this is going to be 1 plus h. So f evaluated at 1 plus h minus f evaluated at 1, all divided by h. Okay, and then we have to find that limit as h goes to 0. Okay, so let's find f evaluated at 1 plus h. And I'm going to do that on the side. Okay, so to find this, f evaluated at 1 plus h, we have to plug 1 plus h into this function. But notice what this function does to any number that you plug into it. It cubes it, and then it adds that to 4 times the number that you plugged in. So if you kind of write this out as a shell, is it cubes the number that you plug into it and then adds 4 times the number that you plugged into it. But the number we're plugging into it is 1 plus h. So it's just going to take 1 plus h and then cube it and then add 4 times 1 plus h to that. Okay, so now I want to cube this out. Okay, and to cube that out, remember cubing that means you just multiply by itself 3 times. And then let's go ahead and distribute this 4. And so you get 4 plus 4h. And now I'm going to FOIL this out. So you get first is 1, outer is h, and then inner is h, so that's 2h. And then the last would be h squared. Okay, and now let's multiply this out. Now to multiply this out, you would just take this 1 and multiply it by all 3 of these. And of course you would just get this. Because you're multiplying by 1, so you get the same thing back. And then multiply each of these by h, and notice you get h, and then 2h squared, and then plus h cubed. And then of course you got to add 4 and then 4h. And now let's just simplify this by adding up like terms. So you have h cubed, and then it looks like you have a 3h squared, and then you have another 3h, plus 4h, so that's actually going to give us 7h, Okay, and then plus 5, right? 4 plus 1, so plus 5. Okay, so that's what f evaluated at 1 plus h is equal to. So I'm going to put that up here. Okay, now f evaluated at 1 apparently is equal to 5, but let's just double check that. When I plug a 1 into here, I do get 1 plus 4, so it is 5. Okay, so f evaluated at 1 is 5, and I'm subtracting that off. And then all of this gets divided by h. Now notice these 5's cancel out. Okay, and so we're just left with h cubed plus 3h squared plus 7h, all divided by h. And then we're going to find the limit of that as h goes to 0. Now, one thing I'd like to mention here is when you do these kind of problems, whatever this number is over here, it does need to cancel out with some number from this part over here. If you don't get those to cancel out, like if you don't get this number here to cancel out, then this isn't going to work. You've probably done something wrong. Now, the reason that's the case is because if I were left with a number here like 5, then it wouldn't cancel with this h on the bottom. And we need this h to cancel on the bottom because notice that when I go and try to evaluate this limit using direct substitution, right now I get 0 over 0, so it's indeterminate. But because every term in the top has an h in it, that's going to cancel the h in the bottom. If I'm left with a term over here that doesn't have an h in it, then it's not going to cancel with this h on the bottom, and I'll still have this problem. I won't be able to determine the limit. So anyway, make sure this cancels out. Okay, in this case it does. And now, when I divide here, this h divides every one of these terms. And so I'm just left with h squared plus 3h plus 7. And now this limit is determinable. Using direct substitution, when I plug 0 in, I get 7. Okay, so this is equal to 7. Okay, this limit, which happens to be the slope of the tangent line right when we're at this point 1 comma 5. Now we're supposed to find the equation of the tangent line at this point. So notice we know the slope of the line, the tangent line, and we know this point goes through the tangent line. And so we can find the equation of the tangent line using our point slope formula. Okay, and m is 7, that's our slope, and then x1 is 1, and y1 is 5. Right, it goes through this point 1 comma 5. Okay, and now let's just solve for y. Okay, so let's distribute the 7, so you get 7x minus 7, and then add the 5 to the other side, and you get 7x minus 2. Okay, so this is the equation of the tangent line to this function right at this point 1 comma 5. Now, just to finish this off, let me show you the graph of this. The graph of this function x cubed plus 4x looks like this. And then the tangent line at this point 1 comma 5 looks like this. 7x minus 2. Now you can see that has a positive slope, okay? And you can see that it goes through, the y-intercept is at -2, right? So it goes through this point -2 on the y-axis. Okay. Okay, so that's it. That's the equation of the tangent line at this point. Now notice if you were to find the equation of the tangent line at a different point, like when x is equal to 2, the equation of the tangent line when x is equal to 2 would be completely different. Okay, so you would have to go through this process again. You would have to find the slope of the tangent line first, using the instantaneous rate of change in f at a formula, right here using this formula. And then after you find the slope of the tangent line, then you could find the equation of the tangent line using the point slope formula. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.